Welcome to the second half of class 11, right? Hopefully this will be absolute last content class, and then we'll start the project, dive into the project. Okay, so recall that I separate data into, despite the fact we have this big data thing, voice, signal, colors, picture, video, text data, and all sort of stuff. My distinction is between what's called tabular data and graph data. The difference is tabular data means the information or the attribute belong to one entity, right? So one data point could be a human being, one person. And so the data attribute is the height, weight, sex, education, salary, location, whatever. Okay? So that data, that information belongs to one entity. So you can always index it with a single index, I, where I is the identity of that data point. Graph data, on the other hand, means that at the minimum, you have this kind of data, this information that doesn't belong to anyone in particular, but belongs to a pair of individuals. So the number of years you and your friend have been friends, this data point does not belong to you. It does not belong to your friend. It belongs to you and your friend, right? So number of friends you have, yes, that belongs to you. But the number of years that you and this particular friend have known each other is always indexed twice. One index refers to your identity. The other index refers to your friend. So it's doubly indexed, IJ. Okay? Now, I did mention that sometimes you see data with two index, like coordinate, right? Of a pixel going down, going across, that's two index, right? But even though it's two index, actually, it just refers to a single data pixel. So you can actually just line them up. Yeah, 1,000 refer to the first 1,000 pixel. 1,001, you just go down one row, and the first pixel is pixel number 1,001, right? Just keep adding. So the pixel reference is two-dimensional because it's convenient, right? Goes down vertically and horizontally, but fundamentally it's a single index. It only refers to one entity. Okay, but friendship, social network, all kind of stuff, these are properties of pairs of individuals. So that's called graph data. Okay, that's what I call graph data. Now, so let's go by definition first. And some of this I started talking already. So a graph in a mathematical sense, okay, it's not a plot. Okay, so now I would never use the word graph for plot anymore. Graph is reserved exclusively for this. Graph, if you're going to have a casual word for it, it would be thinking of network. Again, network, you're not focused on individual, you're focused on relationship. And relationship always has two indices. Relationship between I and J. Okay? In fact, the double index is so important that sometimes you have index between yourself. Okay? I, comma I, for example. But it's still two indices. Okay. So the colloquial word for graph may be network. What's important is that a graph is a collection, actually two collections. It's collection of V and collection of E. Okay? Actually, I shouldn't put bracket around this. It should be like this. V is the collection of vertices or nodes. These correspond to the entities. Again, correspond to the entities, but you're not interested in the entities. Okay, so let's say you have n entities, okay, n entities. Edges is what you are interested in. Okay, so that's called edges, or sometimes called arcs. By definition, you have to keep this V and E, V and E, V and E always, forever. Okay, this will never change. Now, quick question. I have a collection of 20 vertices. How many edges can I have? You have to ask, is the relationship symmetric or asymmetric? In other words, if I and J, it's the same thing as J and I. So being a friend on Facebook is symmetric, right? Another question you ask is, can you have relationship with yourself? If you can't have relationship with yourself and the relationship is two ways, bidirectional. If you have 20 vertices, how many edges can you have? 20 times 19 divided by 2. Right? Oh, I think I should draw a picture, but okay. So think of 20 times 20, that's 400, right? But then you remove the middle diagonal because you can't be friends with yourself, at least not on Facebook anyway, right? And then IJ is the same as JI, okay? So it's half of that. So it's n times n minus 1 divided by 2. Okay? Now, if it's directed, for example, admirer or follower, I can follow J without J following I. That's asymmetric. So getting ahead of myself, but so that's the thing that I'm interested in. Notice I'm not interested in the individual. Now, in real life, think about this. You're looking at the, okay, think of Facebook data. When we say Facebook data, the first thing that you think of is graph data. Is who is friend with whom. Okay? Who is friend with whom? Facebook knows that. But of course, Facebook does a lot more snooping, right? It keeps individual data as well. So you have tabular data on top of graph data. Okay? And they have not just one graph, maybe they have 5 graphs. One graph is who's friend with whom. That's symmetric. IJ is the same as JI. Google also has not Google, sorry. Facebook also keeps another graph, which is directed. I follow J, right? Because just because you follow this person, that doesn't mean this person follows you. So it has an arrow. It's directional. Okay? And okay, so you have tabular data, graph data, directed or symmetric and asymmetric, all kind of stuff. So let's start with very basic. Just forget individual attributes. Forget that tabular data aspect because we did a lot of tabular data already. So we're just going to look at graph data, purely graph data. And just one graph at a time. So one relationship type. Again, a word for the exam is, if I have more than one relationship types, what kind of graph would that be? It would have many channels, right? It's called multiplex. Multiplex. Multi, many, plex, channel. Multiplex, multiple channel. So different connectivity. Okay? So if I say I have students and I have a graph information on who's friend with whom on Facebook, I have another information on who's friend with whom on Twitter, who's friend with whom in class. Okay, we already have 3 channels. That's a multiplex graph. Okay? Too much. We're just going to have one graph, at least for this class. So let's do this. Again, you can follow this with your notebook. Yeah, Shift Enter, right? Now, the reason I put length is because there are many examples. Okay, so when you go to example data, yeah, and then so many things: color, audio. Somewhere down here, there's network data, the network graph. Sorry, see, there are like so many of them. The reason there are so many of them is because a lot of these are chemical definition, which molecule is connected, which atom is connected with which atom. Okay, so you guys remember that chemical data? Okay, so we're gonna do this just network graph only. Okay, and there are how many of them? Starting from American college football all the way down to Zachary Karate Club. By the way, this is one of those earliest social network data. Okay, 20 years ago, this would have been used as a good example, but now so many of them. Okay, so let's say I'm just going to look at this one here. I'm just going to join the first 5, and I'm just going to take the second element. So that's the name. I put in table form. So that's the first 5. That's the last 5. But there are 200 of them. Anyway, of course, I pick. Now, this is my convention. You can follow this or not if you like. Whenever I define something global, I tend to use like big capitals. Like this list, my example network, I'm going to use for the rest of my textbook. So I'm going to have dolphin social network, which dolphin swims with which dolphins. Eurovision vote, which country in Europe votes for which country in Eurovision. Les Miserables, that's which character in the play appears together on stage. Simple food web, who eats whom? Like a bird eats caterpillar or something like that. World Cup 1988, who plays whom? Zachary Karate Club, that's a classic one. Now, the way I tend to do this, and you can use this convention or not, but I think it's a good style, is I make a list, then I put 0 for the one that I would use as the example, okay? So when I can't think of anything, I'm going to use simple food web as an example. So I just define this. Okay. Now, I'm going to say, okay, I'm going to make a network graph. Okay, let me show you what it looks like. Well, basically, I just say association thread, the name, and the example data with that name. So once I've got this, okay, Shift Enter. It'll take a while because it actually goes on the internet, I think. Yeah. Uh-oh. Okay, it's done. So now, for example, if I say example graph, and I put in, again, simple food web, which is my example network 0, I get this. Yeah. Now it's called simple food web again because it's got only how many animals? 1, 2, 3, 4, 12. One plants too. Okay. Right. So sunflower gets eaten by caterpillar, and this guy and this guy. This guy gets eaten by this guy. This guy gets eaten by this guy. This guy, they eat each other. This is definitely directed graph, right? Because yeah, obviously an owl would eat a rat, but not the other way around, whatever. Okay. Yeah. So that's a simple food web. Yeah. The reason I use it as a example is because, well, first of all, it's small and it's got all kind of feature, like it has a beginning, absolute beginning. It has two ends because apparently dragonfly and owls, they're not a threat to each other. Nobody eats them. Okay. And then you have this bird and this mosquito or insect that eat each other. Very interesting. Now, here's the thing. That's the definition, right? What is my V? What are the set of collection? 1, 2, there are 12, right? 12. Now, in this case, it's directed graph, and assuming no cannibalism, doesn't eat itself, how many connections do I have? Remember, how many V's do I have? 1, 2, 3, 4, 5, 6, 12. So how many possible arrows can I have? How many arrows? 12 times 11 divided by 2. So there are 66. Now, the way it's drawn here, what it means is that it only draws an arrow that has a non-zero value. So you can think of this. Well, let's count how many arrows there are. Okay? There are actually 19 arrows. There's 19 arrows. If you don't believe me, you can count visually. So you can think of it as among the 12 entities, 12 animals. Again, you don't care about individual attributes. There's a picture, but that's only used to identify. There's nothing about the height, weight, age, or nothing, okay? Or anything, nothing. So 12 entities, we don't know anything about it, just the name, just the picture, okay, as an identifier. How many arrows do we have? You can say that there are actually 66 possible arrows, of which 19 has a value of 1 and 47 has a value of 0. Okay, now let's do this. Let's look at this thing in detail. Okay, let's look at this thing. Oops. This is the data, right? This is the data. Now, what I want to do is, let's look at the list of edge. Okay, there should be 12 of them. So what function do I use? I use function edge list. Okay, so that should be 19. What if I just want to look at the vertex? Well, I can do that. Use it vertex list. Oops. Okay, so these are the animals. Sunflowers, well, plant. Aphid, that's, I think. Okay, ladybug, chewy, I think that's a bird. Grasshopper, louse, that's the thing you don't want to get. Caterpillar, beetle, mosquito, dragonfly, and mouse. So this is the order that they come in. Okay, so for some reason they put sunflower as the first one. Okay, fine. And this is the list of edges. You notice that this is the thing. Okay, so this thing is, how do I draw it? Escape. directed edge, escape. Oops. Why not? Escape. Why is it so hard? Wow. I don't know what it's called. It's called directed edge. I don't know why it doesn't come. No, it's this guy. Okay. So these are the edges. Yeah. Now what this means is that there are, yeah, let's do this. Yeah. Okay, so that fine, that's a graph. That's a graph. But in order to work with it, I can't work with this symbolic thing. I have to work with numbers. So what do you think kind of numbers best represent this relationship? What kind of mathematical object? Well, you guys remember that vector is a good way of representing individual attribute. A good way of representing relationship would be a matrix, right? So now I have an order that number one, the first guy I refer to is sunflower. Second one is aphid. Third one is ladybug. So let's do this. Let's look at this. Okay. Instead of looking at this, I take what's called AD adjacency matrix. Okay. Now, this adjacency matrix is an array of number, right? It's an array of number. It has, in this case, two values: 0 when there's no connection, 1 when there's an arrow. Now, how come you don't see that? The reason you don't see that is because Mathematica is trying to be smart. It says that of the 66 possible connections, there's only 19 connections. Why keep the zeros? Why not just keep the ones? This is called sparse array. It's just a representation. But if you want to look at it, you can look at it. Okay. Normal. Okay. You don't need the thing upstairs anymore, right? Okay. See? Now, it would be nicer if you put in a matrix form. So instead of normal, just put matrix form. Okay. Right. Now, let's look, guys. Who do you want to look at? Let's look at sunflower. Okay. Sunflower is the first one. So this sunflower, this is information about sunflower. It's not connected to itself, but there's a 1 to aphid. Right? Aphid is the first one. Nothing to ladybug, nothing to towhee, nothing to owl, 1 to grasshopper, louse, and caterpillar. See that? So sunflower has 1 corresponding to aphid, grasshopper, louse, and caterpillar. 1 means it gets eaten by. It feeds. See? Sunflower, grasshopper, louse. What was the other one? Caterpillar and aphid. So this is aphid. Okay. Now, you will notice that in this case, there are two guys who are special, dragonfly and owl. This guy doesn't get eaten. So let's look at the row corresponding to owl and dragonfly. Where's dragonfly? Dragonfly is second from last. See? All zero. Because dragonfly feeds nobody. So IJ in this case means animal or food I gets eaten by animal or food J or animal J. Okay, so this is dragonfly. It's all zero because it doesn't get eaten. Likewise, you look at the fifth row. This is information for owl. It doesn't get eaten. Okay, it doesn't get eaten. Having said that, let's look the other way around. Let's look vertically. The last vertical has to be what? Has to correspond to the last item. That's mouse, right? So this one would be mouse eats what? So mouse eats what? Mouse eats the 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So louse, caterpillar, beetle, and mosquito. Where's mouse? Where's my mouse? Mouse, louse, caterpillar, grasshopper, beetle. Dragonfly, sorry, dragonfly. Oh, this guy is not, yeah. Who's this guy? Caterpillar, grasshopper, yeah. Grasshopper, louse, beetle, caterpillar. Okay. So that's it. That's how it works. Okay, that's the tree of life, so to speak. Okay. Now, so this is my concept of using the function call and go read this up, adjacency matrix. So in this case, again, a graph is a list of edges and nodes. In order to turn it into a mathematical object, the best mathematical object to represent relationship is something that has two indices. And what in mathematical world has two indices? Matrix, right? Now, to use matrix, you have to make sure that you make an assignment of the first element corresponding to what, second element correspond to what, right? So, right. So now, okay, so now I have all this, okay? I already did one for the simple food web. I'm going to do it for 5 more. Again, these are all sparse array. Okay, you can look at them. You can look at them, but you notice the sparse array has information already. Let's go to simple food web. See that? Dimension 12, 12. So that means it's got 12 vertices. So the matrix is 12 by 12. But how many elements is non-zero? 19. Okay. So obviously you can look at this. Now, if you look at this, this is pretty large, 62 by 62. So if I don't use normal and I use something like matrix form, and apply to all them at example adjacency matrix. Yeah, it's going to be very large, right? So that's why I didn't print it out. Yeah. Okay. So. Fine. Okay, so I have all the example. So you can go back. Actually, there's a function down here called adjacency graph. So if the data comes in the matrix, you can turn it into graph. The data comes as a graph, you can turn it into matrix. Vice versa, okay? So if I have adjacent example, adjacency matrix, okay, of what's it called? Network example 2, okay? Okay. That's this. If I apply adjacency okay, I get, you know, similar thing, except this one I didn't have the label. So now this one is okay. I just make a show and tell. Oops. Oh, I forgot to run this line. In the very beginning of this file, shift enter this one, guys. This is nothing more than nice table with a, you know, otherwise I use this once. I use it many times, so I don't want to keep writing table. So go down here. Once you go shift enter that one, then you can use it forever. Okay. There, just makes it a nice table. Okay. Simple food web. This is the adjacency matrix of that. Now, if I want to do list density plot, I can basically do this. So this is kind of like nicer way of looking at 0 and 1. See, when you can see the ones here, right? And the ones here, and that's the color and color. It's the same thing. Okay. Now I can do this for everybody, obviously. Right. So these are my example, guys. These are my example. Social network of dolphin. These are dolphins. Okay. Dolphins are very social animal. So they know that, you know, among the 30 or so dolphin under study, who's friend with whom. This is Eurovision vote. This is Les Miserables. I showed you last time. Simple food web. Okay. Good. Now, this is where you have this property. Now, this is a little bit beyond graph analytics, but it's used in graph analytics. Okay, this is more like mathematical graph property. So I'll just tell you that connected means everybody is connected. There's no isolation. You can get somewhere. Okay. Okay. So the question is this. Okay. Ask in Mathematica, if you have this Q, it's a query. Okay, it's a sign that it's a function query. Is it connected graph? False. Okay, it's not completely connected graph. There's also partially connected graph. Now, if you want to find connected component, you can do that. So this one is connected. This one is, this is a little bit advanced. Basically, look at this. All the dolphins are connected somehow. Okay. In this case, it's not completely connected, but it's connected in this case. So everybody belongs to the same connected component. This is like clustering, but instead of clustering by similarity, it's clustering by connection. So what this means is that all these countries vote for each other. Maybe Andorra and Czech Republic and Monaco and San Marino and Slovakia, maybe they only vote for themselves. I don't know. I don't know why it's disconnected. Here, all the plants and animals are single, but there's only two. There's this guy that's connected. Why? Why do you think that is? It's connected because they eat each other. Okay. So disconnect. So this is connected. Cyclic, acyclic. This is property of graph traversal. You can also do the study here. Question is, okay, acyclic. Acyclic means it goes, it doesn't come back. Is it acyclic? No, it can come back. There's only this thing, World Cup 1988, that is acyclic. Why? Because once you play with somebody, you don't come back. You know, it's sort of like a championship. Sparsity, this is, you already saw that. That's basically, you know, the reason it's chosen as sparsity. Again, this is vertex count, edge count. Okay. Now this is where it gets important. Okay. I have the example. Now I'm going to have layout. You notice that this is drawn kind of arbitrarily, right? If I move this node a little 2 centimeters to the left, does that change the relationship? No, because right now an arrow is just that. The length of the arrow means nothing. Okay, so it's not like the arrow is long, so it's far apart. No, it just randomly, it's just drawn so that roughly it looks nice. Okay. So basically, where do I put this? So this is called graph layout. Now, the word is called embedding. I'll tell you why later. Think of it as the vertex or the entity itself is some nebulous entity. It's something that has properties. But we're going to put it down somewhere. We're going to give it an address. And that address is 2-dimensional. So we're going to embed this entity in 2 dimensions. So think of this word embedding as placement. Okay, but it's called embedding. Sorry, it's technical word for it. So let's try this. There are many ways of embedding, and these are in the Mathematica option list, right? So there are maybe 20 different ways. I'm just going to pick 4. And I'm going to use automatic as a default in this case. Okay. Now, what I'm going to do is I'm going to make this this one I don't need. This is for labeling purpose, right? Remember, I was drawing the picture, and I want to say, okay, this is a mouse, this is aphid, this is grasshopper, right? I don't want to use number, but because it's a matrix, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I create this kind of thing. This thing here as a naming. Okay. So there it is. Okay. So this here, once again, I do a couple of things at once. So I do the plot. There's a graph plot and there's a community graph plot. I haven't told you what it is yet. Maybe I should have told you that before, but anyway, I'm just going to do graph plot. I'm going to use example network, all 6 of them available here. But I'm going to start off with the one that I like, and that's the food web. Embedding method, I'm going to start with automatic, but I can choose any other. Okay, so basically this layout, I can say circular. See that? Basically that puts thing in a circle. Now, has this changed the meaning? No, it hasn't. Okay, it just looks nice. I like circle, looks nice. Okay. Now, I don't like circle, I like rectangle. So I put in a grid. Fine. It still has the right relationship, right? There's still Chewy and mouse eat each other. I change it to layer digraph. Okay. Maybe this one is a little bit more clear, right? More structure. It's kind of like layered going down, and this thing eats each other. And this thing called, I don't know, spring embedding. This is like, imagine that each link is a spring and just sort of boing, you know, let everything go free or something like that. So these are kind of like display option. Okay. Now, obviously, I'm not here to make things just look pretty. So this will mean a lot more than just looking pretty later. Okay. But right now, completely arbitrary. Arbitrary, right? Right? There's no reason why I shouldn't put ladybug sort of like in top right corner. As long as the arrow points correctly, okay, this is completely elastic. Now, Obviously, this is elastic because I just want to know who eats whom. However, and this is where the data set comes in, I download this data set that I prepare. There are two data sets. I'm just going to do, okay. Now, in this case, don't worry. The difference is, in the example before, I load the graph data and I create adjacency matrix. In this case, the data comes in the form of adjacency matrix. So that's why it starts with this word, adjacency matrix type province. What it means is I'm going to take a matrix of 70, you know, Thailand has 77 provinces. Okay? You live in Thailand, you should know. So the matrix is 77 by 77. The connection between provinces are defined, in this case, by sharing province border. Okay? So if you get from province A to province B without going to the third province, there's a direct border. I consider that connected. Question. Is this matrix symmetric? Yes. Because if you can go from one province to the other, you can go the other way around. Right? It's not like immigration flow where, you know, one country go to the other country can't come back or something. Okay? This is bilateral, right? You go from Jangwat or province A to B or B to A. So how many, and Jangwat is not bordering with itself. How many possible edges do you have? Again, you divide by 2 because it's symmetric, right? 77 times 76 divided by 2. Okay? Now, actually, let's collect that. Now, the name is here. So these are kind of from the data set. I just happened, the reason you have this, you know, from the second column, third column, it has to do with the data. So if the data comes like this, that's how you reference. Okay, fine. So now, so I did this. Again, this is for naming function. The way the file comes in is alphabetical. So Amnacharath starts with A, so it's the first Jangwat, first province. And Yasothon is Y, it's the last one. Bangkok is number 3. Okay? So this is my naming. Fine. Now, I'm making extra calculation. Let's look at this data set first. What does it contain? This data set has 77 provinces. Okay? Come on. Okay. Oops. Should come out. Okay. The first sheet, it's got the names and it's got the adjacency matrix, right? You will notice that this adjacency matrix is completely what? Symmetric, right? So you can see that Chachoengsao and Bangkok are connected. And so Bangkok and Chachoengsao are connected. Okay. So number of edges. Now you go to this one. Now I just told you, right, in the previous case, the graph, the location of the vertices is arbitrary. What if it isn't? What if I want the location to mean something? Obviously, Jangwat, the location can be physical. In this case, this is called physical latitude and longitude. Okay. Now, the other page also gives you 2 numbers, except this is from a machine learned graph embedding. It's done separately. In fact, this is done using a GitHub Python function. Okay. But anyway, the point is, those are locations in 2 dimensions. So now I'm going to calculate, okay? So what's the minimum province? So these are basically, these are the latitude, longitude, guys. Okay. See that? So that's the minimum latitude, sorry, longitude. Minimum longitude for Changwat in Thailand is 98, maximum is 105. Minimum latitude is 6. Highest point, Chiang Rai or Mae Hong Son, I think, is 19. Okay? So because we are both equator and we are east of London, everything is a positive number. Okay? Right. Now, this is a ratio because I want to say how tall Thailand compared to how wide is Thailand. So I take the first, the latitude difference divided by the longitude difference. So this becomes aspect ratio. So when I do the plot, I maintain this ratio. Okay. This is what I did. Now, first of all, there's no connectivity here. There's no connectivity here. I'm just listing the location, geolocation type province with the name. Aspect ratio is equal to 1.95. So you can see, right? This looks like Thailand. If you know the province name, this is where we are back up here. You go down south. Okay. Surat Thani is here. Phuket is here. Go to Chiang Mai, Chiang Rai, right? Okay. Now this is just using the second sheet, right? Because I'm just giving the location. Now what I want is actually plot interconnectedness between different provinces, but locate the points not arbitrarily. So this is what I did. Okay. So first of all, I can do this. Okay. Now, I don't show anything. Let's do this. It's just gonna give connection. Okay, some kind of connection. It's got a name. Well, we can take the name out actually. See, it kind of looks a bit like Thailand, but it's not quite. Why isn't it like that? It looks a bit like Thailand is because the provinces are kind of in the right order because they connect. You can go from Changwat 50 to Changwat 13. 50 is probably Ranong, 43 is probably Prachuap or something. Okay, but it's not quite. So by introducing this, okay, this is just a name. By introducing vertex coordinate is given by the geolocation. I get that. Okay. Now, what's cool is this location is in 2D, right? I can do something else more interesting. For example, let's say the X is the longitude, the Y is the latitude, but I want to plot in 3D, and the Z dimension is rainfall. Can I do that? Yes, I can. Okay, I haven't done it here, but you can see that the 3-dimensional looks a little bit like this, right? So now I can make the height corresponding to maybe elevation above sea level or something like that. That would be more interesting. I haven't looked that data up yet, so it's not done. So you can see that this is an interesting thing. Now, I told you that this chapter is about graph analytics. And so far, we've done graph analytics without machine learning. Okay, without machine learning. Okay, there is a thing called machine learned graph embedding. And the example, I'm just going to show you the result. Okay, it looks a little bit like this. What it does is that if you think of traveling from one province to the other as being effort, this is how the machine learning has put provinces that are close together. So it takes you a lot of effort to go from Chumphon to Loi, but it takes little effort to go from Chumphon to Surat Thani, for example. Okay, but anyway, this is more advanced. This is what's called graph neural network, graph embedding with neural network. Okay, I have it here, so I might as well show you, but I don't want you to pay too much attention. Okay, now, so let's go one more step. This one here, let's go back to the same thing, right? The ladybug and who eats whom, dragonfly, and let's use a spring embedding layout. Okay, fine. Or let's look at Eurovision votes. Yeah, see? Oh, you know what? The reason Monaco is isolated because I think Monaco votes for other people but never votes for itself. Yeah. Whereas Georgia never votes for other country, but everybody votes for Georgia. So it's kind of like isolation. Okay. It's a one-way thing. So anyway, let's look at something more interesting. Dolphin. Let's look at dolphin. Okay. And this is the one I think I'm going to use for the final text paperwork. These are actually names of dolphin. You know, people who study marine biologists, they can actually recognize individual dolphin. And these are like 60 of them, I think. So some of them are not interesting. It's called SN89, but some of it is more friendly. Not maybe has a feature, quasi, trigger, bumper. Maybe that's a behavior, like to bump into the boat. Okay. So some of it's got, you know, nice names. Zia, white tip. Okay, some dolphins just have numerical alphanumeric name, not that interesting. Okay, now here's the thing. I show you just now, right? I take the whole country of Thailand and sort of like make an effort-based location. I can do that here using what's called community graph plot. So you can imagine that here, right? There's like clustering. Think of clustering, right? But instead of clustering in physical distance, because after all, this is not physical distance, this is not physical location. I can put them in anywhere I like, right? So I can't do clustering based on distance. The distance means nothing because in one graph, these guys are close together. In another graph, it's not. Okay, so can I do clustering based on distance? No, I cannot. However, what I can do is clustering based on edges. The more edges you have together, the closer you are. This is very advanced. So now let's think of clustering, okay, in a way that depends on some kind of algorithm. So this is kind of like unsupervised learning. And in Mathematica, it's called community graph plot. Okay? Or find graph community if you want to list the element. For example, in this case, you can see that dolphins are not universally friendly to everyone. Maybe there's a little bit of a niche going on. Okay, so that's a group of 10 dolphins that tend to hang out together. There's another group of dolphins hang together, and these two kind of like maybe they are together, but they don't really hang out with anyone. And you can do this with any kind of relationship. So let's see Eurovision votes. Yeah, that's kind of like 2 groups, 4 groups. This is a musical, right? So let's look at that. So, maybe there are 5 kind of cluster. Maybe there's subplot going on here, involve all these people. Simple food web, right? Simple food web. So you can see that these are kind of like intermediate guy, maybe. It's a hunter, or I don't know. This are kind of World Cup. World Cup, right? This is kind of like these countries maybe play together a lot. Maybe they're in the same group. Yeah. This one doesn't have name, so just that. Okay, you can do this kind of analysis. Now, bear in mind that this is only good for very small network. If you have a large network, for example, I'll show you example here. Something like, I think there's a medical data that I have as an example somewhere here. Anyway, it can be very large. So you can't see very much. So this kind of analysis would work, when you have maybe 50 nodes or something. So you literally, as an example, you can say who's on individual pairwise line between this class, right? So if I'm doing clustering based on where you sit, obviously it's these two, right? But if I have an information on who's friend with whom on Facebook, I can see that, oh, this class actually separate into 3 clusters. But that cluster is not where you sit. It's where you are. Sorry, it's how your relationship is on Facebook. Okay, so maybe this is a type group. So this is a form of unsupervised learning that you already see. This is just about it. And now we'll go to the major class of unsupervised learning on graph called centrality analysis. Now, I briefly mentioned to you already what those are. Okay, there are local method, meaning just score who is important. This is the sort of like centralness. Who's the key person in this network? Think of you're trying to infiltrate a criminal network. You would like to know who is the linchpin, who is the mafia connection, the guy that basically connects everyone, okay? Or a terrorist cell, because terrorists are not hierarchical organization, be too easy to detect. So terrorist cells are kind of like semi-independent network of operators. If you want to bring down, you don't want to bring down just one cell. You want to bring down the whole network. Which cell is kind of like sitting at the crucial junction point, where if you infiltrate this cell, boy, you've got intelligence on all the terrorists of this network. That's what you want to do, okay? This is called centrality analysis. Now, if you go back and look at this, let's go back and look at this. Yeah, let's look back at original graph plot. Okay. Okay. Now this graph plot, if you think of this as a terrorist cell, okay, if you have enough resource to penetrate one cell, would you penetrate cell number 17? Right? That's a bit of a waste of time, right? But cell number 1 looks good. Maybe cell number 32 looks good. Right? Right? But if I plot it like this, it kind of gives you the picture. But if I plot it like this, who would you go after? Well, the obvious one would be number 1 and number 34. Why is that? It's obvious because it's got more edges, right? That's called degree centrality. If all you do is count. Okay. But certainly, let's go back to this picture. Let's go back to the picture. Let's say this guy, number 22, has 2 connections. So does number 17. Between 22 and 17, which one do you think is more in the thick of things? It's obviously going to be 22, right? Even though, so counting number of connection alone is not good enough. So that's why you have more advanced technique. This local technique is too primitive. So let's do eigenvector centrality. Eigenvector centrality And in a machine learning class, you go into detail why it's called eigenvector centrality, because it's based on calculating eigenvector decomposition of the adjacency matrix. What it means is that you are important in the network if you have a lot of connection with people who have a lot of connection, who themselves have a lot of connection with people with a lot of connection. So it's a recursive equation. This recursive equation ends up formulating a matrix equation that's solved as an eigenvalue decomposition. That's why it's called eigenvalue. This is the one that I use and introduce, one of the first guy in Thailand, if not the first person, to use that to analyze connectivity between Thai commercial banks. Okay. Now, this is an excellent technique. However, it failed in one case like World Cup. That data doesn't work because what happened is when you do this recursion, it just keeps flowing. The value just go to zero. Okay. So to fix this, a better version, a more robust version is called CAT. CAT has a parameter that adjusts the way the algorithm works. Then you go to PageRank. PageRank is like a version of CAT that has a fixed parameter, but a better, maybe even more parameter, but fixed. So by default, I tend to use PageRank for everything. Okay. I would like to use eigenvector because it's a nice centrality, but if I don't use that, I use PageRank. Incidentally, PageRank is named after Aaron Page, who is a co-founder of Google. Okay, this is how Google ranked the page. So you have to go as your homework, read this article. Okay, I'm not gonna give you homework on it. I'll just ask you on the exam how Google used this centrality to basically win the world. Okay, it's in here. So you go to Google, it's in here somewhere. So this paper will be on the exam, but not homework, because I feel like it's too soon to give homework. Okay, that's in the line group. Now, there's something else called betweenness centrality. This is very nice. And this is based on the idea that, again, this thing would work for something like what? Like the geographic network, right? Because here, the notion is this. The notion is take any two jangwat, any two provinces, find the shortest path. In this case, let's just make shortest path the minimum number of province to cross, okay? Not physical road. Calculate that for every pair. And therefore, every province, ask how many shortest paths goes through you. The province that contains or sit in the middle or is part of the most shortest path wins. So in that case, let's do that. Let's do, now this part I haven't written in the code, so that's right. So betweenness centrality of, okay, adjacency by province. Oops. Oh, sorry. That should be the graph. Yeah, so I take the matrix. I have the matrix already. I have to make it into a graph first, sorry. Okay, remember the adjacency matrix kind of like a data. So that's it. That's the importance. Now let's bar chart it. Let's bar chart this guy. Okay, and let's give it name, right? Chart label. What's it? Vertex names. What's it? I use the word vertex name type problems. Oh, it's too big. Let's I have to rotate. Oh, I know how to do this. Hold on. Bar chart. I can make it sideways. Plot style. Side, no. Charts. Chart style. Something like sideways. Hold on, I have to look at the F1. Can I go F1? No, can't do that. Just front height maybe. No. Front height. Maybe just simple style. Oh, I know. I use it later. Sorry. I use it later somewhere here. Yeah. Okay, let's do that. Okay. Sorry. Okay, let's go ahead. Use it. Okay, so centrality method. Okay, I do the same thing. I have a list of centrality method. One is a default. I do this for all the centrality, and voila, there it is. Okay, so this one happens to be for, sorry, I didn't do this for country, for province, but it works the same way. Maybe I should add an example. So sunflower, towhee, and alf. So it turns out mosquito is more critical. Okay, so let's turn it to betweenness centrality, and let's think of play. Yeah. So to get from one character to the next, sorry, I can make this larger. To get from one character to the next, chances are you have to pass through this guy, Lao Qian. I don't know. Have you seen the play? Do you remember? This is apparently a very important character in this play. Okay. If not, then let's go to Dolphin Social Network. So if you want to spread gossip amongst dolphin, right? You should gossip to SN100. Okay. So in terms of passing the message from one to the other. Okay. So this is kind of analysis that you can do. Okay. Normally, when you did this, you would rank it. Remember, I showed you last week. I did this with actor. Remember that? So instead of having 66 dolphins, I say who's the most central actor or actress in Hollywood, and I rank all 150 of them. And there's one person who's really very important. It's like he's in all the important movie because he's in a lot of movie with people with a lot of movies. Okay. Have you guys figured out who that is? No? Okay, I won't tell you. You have to watch the video. Okay, so that is how we do unsupervised learning. Why is it called unsupervised learning? Because there's no right or wrong. There's no label that say who is the most important. The definition of who's the most important depends on your definition. Do I say this guy is central to the network because he knows a lot of people who knows a lot of people who knows a lot of people? Or I say this guy is important because for any pair of connection, the shortest path invariably pass through this guy. He's like a middleman. You know, the gossip goes through him all the time. So if you talk about passing on gossip, this guy is good. This guy is good. Okay, so if I'm gonna create like a gossip among dolphin, I should go to SN 100. If not, I should go to B scratch. Okay, cross doesn't matter, cross doesn't pass information, that sort of thing. Okay, so these are machine learning based, but it's sort of like an algorithmic machine learning, not neural network kind of thing. Okay. Finally, and the last thing I'm going to cover today is to say, wait a minute, there are data analytics that are purely based on algebra. You don't need to do any kind of clustering. You don't need to do anything. You just do matrix multiplication. And this gives you a lot of insight. And some of that is very useful. Yeah. Now, first of all, I have this function in blue. This is just going to help me format the graph to make it look nice. So just shift enter, don't worry about it. Okay. The first thing is matrix power. Matrix power is nothing more than matrix multiplied by matrix. Does this require any kind of machine learning? No. Okay, it's just a computation. So I can multiply 2 times, I can multiply 5 times, right? In this case, I give an example. Now, here's the thing. Here's the thing. Can you see this? You see this? This is a matrix 1, 2, 3, 4. If I take 1, 2, 3, 4 times 1, 2, 3, 4, 10 times, I get this. Obviously, the number gets bigger, right? In fact, if I take it infinite times, see, mathematics, I can do analytical, right? So I put in infinity here in the limit. It goes to infinity. Okay, fine. Not too interesting. It just blows up, right? Conversely, let's have another matrix. Let's have another matrix that is like this, but 0.1, 0.2, 0.3, 0.4. Let's go 0.1, 0.2, 0.3, 0.4, okay? If enter, look, if I multiply 20 times, 50 times, 100 times, it gets smaller and smaller. No surprise there, it dies out. But I'll show you something special with this guy. This guy is a special matrix. When I multiply by itself, it doesn't blow up. And in the limit, go to infinity, it doesn't go to 0. See? Earlier example, you either go to 0 or you go to infinity, right? This guy doesn't go to, in fact, it goes to what's called a steady state. Meaning, if you keep multiplying this thing by itself, it's going to stay by itself. Where do you think that is the situation? That situation, if you talk to your friend in the economics department, is called equilibrium. Okay? This is the equilibrium. Now, what is the equilibrium? Equilibrium what? If you notice, okay? In this case, the rho adds up to something small and it goes to 0. And if I have this, the rho adds up to something bigger than 1, it goes to infinity. Right? Goes to infinity. But this guy, the rho adds up to what? Exactly 1. This is my trick. If the rho adds up to 1, 0.9, 0.1 adds up to 1, 0.6, 0.4 adds up to 1, when you multiply that many times to infinity, you settle down at number 0.4, 0.6. That's interesting. That's interesting. How can we use this? Let's put it this way. Let's say you have a girlfriend or boyfriend. she's in two states, bad mood, good mood, or good mood, bad mood. Two states, good mood, bad mood. If she's in good mood and she has probability 0.1 of staying good mood, 0.9 of going from good mood to bad mood. If she's in bad mood, she has 0.6 probability of going from bad mood to good mood. If she has bad mood, she has 0.4 probability of going to bad mood. And this is talking about the next day. Okay? If this is your girlfriend, it doesn't matter what mood she's in. If you marry her for more than 100 days, if you marry her, you stay with her for more than 100 days, you can bet that every single day from there on out, she will have 0.4 probability of being in a good mood, 0.6 probability of being in a bad mood. Forever. This is her equilibrium state of mind. Okay. This kind of thing is called Markov chain from a mathematician named Markov. The reason it's called Markov is because this transition probability, this thing here is called transition probability, stays fixed and keeps on forever. And equilibrium probability is 0.4 and 0.6. So that's one application. This application, you can do statistics already without doing any statistic because you know the matrix can multiply. Okay, so that's one application. This, by the way, is one of the, okay, I just say it casually, you know, matrix Markov chain. I just say, oh, it's just a Markov chain, just apply it here. This here makes not make so much money. A lot of financial professionals spend their entire life in this. Okay? In particular, have you guys ever bought, do you know what a bond is? Okay, a bond is a borrowing by an institution of government. Okay? It has a fixed coupon, say. So there's no risk. But there is a risk. There's no small risk like price going up and down. Okay, you always get 8% a year, 8% a year, 8% a year, no problem. But there's a big risk. That big risk is actually goes bankrupt. So there's a probability of default. Now, historically, probability of default is not defined numerically. It's defined as a rating. So very high probability default would be something like D, bad grade. A little bit better than D is C. A little bit better than C is CC, 2C. A little bit better than that is triple C. Think of it as C plus C minus. Better than that is B, double B, triple B. Think of it as B plus B minus. Think of it as, and then better than that is A, double A, triple A. Now, if I line them up, how many states have I got? Well, actually, there's a final state called bankruptcy. Okay, let's say D is bankrupt. D is bankrupt. So how many possible states there are? There are actually 10, right? A, B, C, and D. 10 states. At the end of every year, the bond that you bought, maybe you bought it, it has a probability of default corresponding to B grade. What happened at the end of the year is bad news hit the company. Evergrande, sorry. Okay, well, Evergrande is bad example because that's already D. But before it was D, 5 years ago, Evergrande went from A to B, maybe it went to double B first, and then went to D. These are all transition probability. So a big chunk of what's called credit analysts, people who work in financial market in fixed income or bond or government bond, they basically spend most of their lives in Markov chain. Now, some of them will try to make it fancier by using non-Markov chain, okay, or some kind of Markov process. These are fancier things. But here, you know, you can say that for 100 years, more than half, maybe 60-70% of people working with bond play with Markov chain in one way or the other. Okay, but it's not finance class, so I'm going to skip that. Yeah. Now, this is where it gets interesting, but I don't think I have, much time left. There's ownership propagation. Basically, this inner product, if you think about it, okay, this is such a nice way of doing things. So let's say 1 owns B, 2 owns 3, and I want to know if 1 owns 4. So basically, the ownership, if a company A owns 60% of company B, the company B owns 3% of company C. How much do I own? This is legally defined. So I take the ownership matrix, multiplied by itself, so I get it to the second generation, third generation. Okay, and there are more advanced version where I do sort of like sideway and that sort of thing, and that's in the article. But anyway, so we kind of like running out of time, but this is what it would look like. Okay, so if I keep something like, who owns whom, propagate downward at the end of the story, this is where we end up with. Now, this thing, by the way, in the article, which again, I will not ask for the homework, I'll instead just leave it for the exam. There's an example where this is actually from real life, done here. I was contracted by a revenue department of Thailand, right? In collaboration with Business Online, which is a partnership with the school. So we were doing this kind of calculation about cross ownership and that sort of thing. The thing is, you want to know if companies that look like separate companies, in fact, are on a conglomerate basis, very closely tied. So if they're closely tied, they can use supply chain within them to sort of like hide profit. Okay? It's very simple. Okay, it's a very simple concept. If I own 2 companies, one company has a 5% tax rate, the other company has a 10% tax rate. I'm going to make the one that has a 10% tax rate looks like it's losing money. Okay, and the one that has low rate looks like profitable. I can do that by coordinating their pricing, what's called transfer pricing. The likelihood of me being able to do this depends on how much I influence them. The influence comes from ownership. And the ownership can only be calculated by, sure enough, multiplying matrix, either once, twice, or infinite times. Okay? Well, usually you don't have to go to infinite times. So numerically, you just multiply matrix 5 times, that's good enough, or maybe. Okay? I'm not giving you any detail on how it's done. The fact is, this is real life example. This is real life example. So supply chain consolidation, calculating whether or not, so if you want to calculate things like how important is China to the world supply chain, are you just going to look at how much China export? Or are you going to look at how much of China's export becomes component of that second country's export to the third country, which then becomes component of export to the fourth country, right? So that's not tax or ownership. This is export network. You can do that, right? You can do that with, again, a criminal network, terrorism network, any kind of network where you have a structure that propagates. You can do matrix multiplication. So it's very, very powerful here. And this here doesn't, again, it doesn't require machine learning. It's just multiplying matrix product. Okay. So you can read, basically the text is a description of the workbook, but I haven't put it in here. So read that, I'll ask for the example. Okay, so I think I've kind of like managed my time pretty well. I want to be on the dot. Hey, I'm on the dot today, so very good. Good. So next week, DB2 is gonna randomize the order. So between here and now, you have to register your team name, whatever, with, okay? And then on the day, you will randomize, you will call up, don't tell them beforehand, okay? Say, group, you can use dolphin name if you like from here. You can use whatever you like, okay? Now, imagine you're trying to win me over. How are you gonna win me over? Think about that hackathon. It's gonna be real important problem with impact. It's gonna be interesting use of data analytics. Not more importantly, but thirdly, for me, it should demonstrate that you are using what you learn. Okay. Now in hackathon, you don't have that final criteria, right? The criteria is that it solves real business pain point. It's got good business model. It can be monetized. This is something that can be valid. The data makes sense. You can rely on it. All kind of quality stuff. But in this class, another criterion is that I would like to see that this project is an evidence of you being able to use what you learn. Okay? So that becomes very important. Okay. So how many, we'll work on it. You do the survey on how many groups, how many teams, and we'll work out on how much time you have left. And then from now on, hopefully we'll just be doing like workshop and workshop and workshop. Okay? And some of you can sort of like use this as a seed for your project, capstone or something. Maybe not, maybe not. Okay? Up to you guys. Okay, so everybody's got a team, everybody's got a working schedule and basic data set. It may well, now be prepared of this. After next week, I may actually tell you that this data set is not interesting enough for the project. Okay, so don't bet on this being approved. It's like, oh yeah, think of it as an approval. You're not just pitching to see who gets, highest score. I might actually say this data set is not good enough to demonstrate what you learn, and you go have to find new data set. Okay, so I'll see you on next month. Right?